Let's start these notes with just a little bit of a warm-up here. You'll need to pause the video. I'm going to go quick, so you need to pause the video and get this all put into your notes before I start talking here. You guys can also rewind as much as you need. So perfect squares. So any number that's squared, the result is what we call a perfect square. So for example, 0 squared is 0 times 0, which is 0. 1 squared, 1 times 1 is 1. 2 squared is 4. 3 squared, 9. 4 squared, 5 squared, 25. 6 squared is 36. 6 times 6, 7 times 7, 8 times 8, 9 times 9. These are all examples of what we call perfect squares. All the way up to 12, you should memorize these. At least these 12. Okay, you'll see these a lot. You should commit those to memory. So if I say, what's the square root of 121, you should know that that's 11. Perfect cubes, well, any number times itself 3 times. So 0 times itself 3 times, still 0. 1 times itself 3 times, still 1. So notice how 1 and 0 are both perfect squares and cubes, right? 2 cubed is 8. 3 cubed, 3 times 3 times 3, 27. 4 cubed is 64. So notice how 64 is a perfect cube, is also a perfect square. 5 cubed is 125. 5 times 5 times 5. 6 cubed is 216. 7 cubed, 343. And 8 cubed, 512. You should probably get used to those as well. Okay, so perfect squares and perfect cubes. Again, pause the video and get this all written out before I continue here. Title, essential question, everything always on the screen needs to be in your notes. Go ahead and sketch these charts right here and fill these out. So you have some values for x. What you need to do is tell me what is the cube root of x. So the cube root of 0 would be 0. The cube root of 1 would be 1. Why? Because 1 times 1 times 1 is still 1, right? So the cube root of 1 is 1. And go ahead, you can use a calculator for these ones as well. So what's the cube root of 2 and 3 and 4 and so on. These ones here, x cubed, right? So 0 times 0 times 0. Square root is not the same as square. It's the opposite, right? And you can use a calculator for the cube roots and the square roots, right? These ones you should probably be getting close to memorizing, at least the squares. The cubes, you might need to use a calculator. But go ahead and fill that chart out as well. Okay, so let's get into it. We're going to talk about parent functions today. Our essential question is, what are the different parent functions and how do we graph them? A parent function is the simplest function in a family of functions. Today we're going to graph 6 of them, and it's going to help to graph them side by side, not all on the same graph, but just kind of one right next to each other. So that way you guys can see what the similarities and the differences are between them. Next screen, again, everything you see needs to go on your notes. So you need to be drawing a graph. And here is the parent graph for a linear function. Y equals x is what we call the parent graph. So for the following x values, figure out the y values and then graph. So for example, when I plug in -2 for x, what do I get for y? Well, if y is equal to x, then y will always be the same as x. So when x is -2, guess what y is? -2. And if x is -1, y is -1, and so on, and so on, and so on. Right, so these are your values for your table. So you're going to take them over here and go ahead and plot them on the graph. So -2 is here, -1, -1, 0, 0, 1, 1, and 2, 2. So you can see that makes that line. This is what we call the parent function or the parent graph for a linear function. And it's going to look like that. The vertex is what we call a critical point. So that's 0, 0, right? And that's especially a critical point because that's exactly where it crosses the x-axis and the y-axis. The key features of this is it is a straight line. It has a constant slope, right? Anything linear will have a constant rate of change, and it increases from left to right. That means it's increasing. It's going up from left to right. Next parent graph is y equals x squared. Again, draw your graph, pause, take the time that you need. How are we going to graph this? Let's use a table. So let's start with these same x values, -2 through +2, including 0, and let's plug those in for x. -2 plugged in is +4, -2 squared is 4, -1 squared is 1, 0 squared, 1 squared, and 2 squared. Notice how the values start to repeat, right? So right when we get here, so notice how -1 and +1 have the same output. -2 and +2 have the same output. And that is the parent graph of a quadratic function. It's the most simplest graph there is for a quadratic function. Y equals x squared. The vertex is the critical point. You'll notice how the vertex is right here. That's at 0, 0. The key features of this graph is it is a parabola U-shaped graph, and it is symmetric across the y-axis. So the y-axis is the axis of symmetry. It's in the first and the second quadrant only, and your a values are greater than 0. So a must be greater than 0. Why is a greater than 0? Because our graph is opening up. If our graph opens up, your a value must be greater than 0. And it is. A is 1, right? 1x squared. Next parent graph is a cubic function. Let's start with the same x values in our table and let's plug them in. So y equals x cubed is what we call a cubic function. So let's figure out what this parent graph looks like. If we plug in -2 and cube it, so -2 times -2 is +4, but I have to multiply it by -2 again, so it's actually -8. So when I cube a negative number, the result is negative. -1 cubed is -1. 0 cubed is 0. 1 cubed and 2 cubed. If you plot those points, it's going to look like this. So you have -2, -8, which is down here. There should be a point right down here. And then you have -1, -1, 0, 0, 1, 1, and 2, 8. And it's going to be kind of a curve, kind of like a parabola, but a parabola is a U shape, right? But it is a curve. This is not linear, right? So we want a curve shape that is going through the points. So the critical points in this graph, well, the vertex is a critical point. That's 0, 0. The key features, it is kind of an S type of shape graph, and it's in quadrants, only in quadrants 1 and quadrants 3. Those are some key features about this graph. And this is the parent graph for a cubic. Next one we're going to do is the parent graph for an absolute value, which is y equals the absolute value of x. Same thing, we're going to use a table, and let's just go ahead and plug in some input values for x. If I plug in -2, I must take the absolute value of that. The absolute value of -2 is +2, so therefore y equals +2. When I plug in -1, it gives me an absolute value of +1, right? The absolute value of -1 is +1, therefore y equals 1. 0, well, that's just 0. Notice how when I plug in 1, the absolute value of 1 is still 1. Remember, definition of absolute value means distance from 0 on a number line. Therefore, -1 and +1 have the same absolute value. They are both the same distance from 0. So what is the absolute value of 2? Hopefully you're thinking +2, you would be right. Let's go plot those points on the graph. You guys should be doing this ahead of me. You should be pausing me, doing this on your own, and then seeing what it looks like. We're going to have -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. So it's going to look like that. So the graph of an absolute value graph is not curved. It actually is two lines, kind of, right? These are straight lines. These are not curves. Kind of V shape, so we'll talk about that in the key features. Vertex is the critical point. Once again, that's 0, 0. And the key features are, like we said, it is V-shaped. It is symmetric across the y-axis. The y-axis is our line of symmetry. Remember, symmetric means that it is symmetric means that you'll have a mirror image on both sides. So you can see this side and across the y-axis They are mirror images of one another, just like a parabola would be. And that's what we call symmetrical. So this is symmetric across the y-axis. The y-axis essentially is your line that cuts the graph exactly in half. It opens up. We have straight lines, like we said. And the key features is that this graph is in only the first and the second quadrants. Our next graph is the parent graph for a square root function. So we have y equals the square root of x. Let's use a table. Well, let's plug in some values and see what we get. If I plug in -2 for a square root, we get nothing. It is undefined. We cannot have the square root of negative values. So that's why we just put a little dash line there. You can also write undefined if you'd like, but there is no value. Same thing for -1, right? If I plug in -1, no square root. What's the square root of 0? Nothing. Well, that's nothing. The square root of 1 is 1, because 1 times 1 is 1. The square root of 2 is not a perfect square, so we're going to need a calculator for that one. Go ahead and punch that in your calculator and see what you get before you continue the video. Oh, notice how the square root of 2, you should have gotten some weird decimal irrational value, right? So it's going to be hard to plot that on the graph. So when we use square root functions, we typically like to use nice perfect squares to plug in, right? Because it's going to give us nice whole number answers, right? For example, 4. What's the square root of 4? 2. So we typically like to use values for square root functions that just make it easy on us, right? We could use 2 if we wanted. It would just make it a lot harder to really plot that on a graph. So this just makes our life a little bit easier to use values that are advantageous to us. Let's go ahead and plot these. So we're not going to plot these first two, right? Because these are undefined. So we're only plotting these three. So 0, 0. And it talks about there, since we didn't use -2 and -1, let's include the values that are perfect squares. All right, so you can also use some other values that are perfect squares. So we stopped here, but let's throw in some other values that are perfect squares just so we can get some different outputs as well. So for example, 9 is a perfect square, right? So if I plug in 9, square root of 9 is 3, square root of 16 is 4. So now we have 5 different points we can actually plot here. So we have 0, 0, we have 1, 1, 4, 2, 9, 3, that's going to be way over here. And the last one's going to be 16, 4, which is going to, we don't actually have to plot that. That's like way too kind of far off our limited graph here, right? But we can kind of see where this is heading. So this is not, as you can see, this is not a straight line. This is a curve. So you want to make sure you're sketching a curve. Make sure you include an arrow at the end, right? Because this will continue on forever. Vertex, the critical point, 0, 0. Once again, that's what we call our critical point. The key features, it's kind of like an eyebrow graph, if you will. It increases from left to right. So as x is increasing, y will continue to increase. You do not have arrows on both ends. You only have an arrow on this way. It's going to continue to the right infinitely, right? But we have a restricted domain here, right? It can only go to 0, right? Once we get past 0, we get into negative territory, which we talked about was undefined. The last paragraph is the cube root function, so y equals the cube root of x. So we're going to plug in some values here. So these first numbers did not work for us. These are not perfect cubes, right? So just like the last one, we want to use numbers that are advantageous to us. So these are the values we want to use because these are perfect cubes like we talked about in the beginning, right? So I'm going to go kind of quick here because I'm running out of time. I have to keep my video under 15 minutes. So if I plug these values in, these are the values I'm going to get for y, and we're going to plot these on the graph, and that's what they're going to look like. So you can see we have a nice curved, kind of like the cube root function, right? That one looks like this, right? So think of it as this one turned kind of on its side. And that's kind of exactly how you can think about it, right? The vertex is the critical point, and here's some key features. It's similar to y equals x cubed, but it's the inverse. And we'll talk about that more later in this course. The last thing I want you to do for these notes is to write a summary. Go back through all 6 of these graphs and compare them. What do they all have in common? What do only some of them have in common? And which graphs have you never seen before? Write a good paragraph summary and turn these notes in.